Okay, all this is great. As I told you, like we can scale these things or we can use the same idea for all the different types of meta models as well. That is quite possible, that is not a problem. The usual question is, now that we have discussed all these things, what is the meta model that I would like to use, or what is the meta model that I should use? It is the same question as your number of samples, cannot be answered, or probably there is no answer for that as such. Someone, if I like kriging, I say kriging. If he likes polynomial response surface, he will say polynomial response surface. That cannot be a uniform meta model for all the problems that you are looking at. So be it. Just people have given some overall perspective on what each meta model can do and things like that. So we will see what this one is. Okay. So it is a very interesting classification here that they are giving. So the first one is kind of comprehension. Let us go through the table headers first. What does comprehension mean? It is more like an exploration. Can you give me a comprehension of the design space? And this is more from an optimization. I want to exploit it. How the way that they are doing this is sample plan to infill points ratio. Please remember, I told you first training samples and testing samples. Like that, when you start the project, you know how many hours of computations you can run, 100 hours. Now you decide how many of that you want to use it for exploring and how many of that you want to use it for exploitation or adaptive sampling or sequential sampling. You cannot go beyond that. You cannot say, okay, let us start with 50 and then I will keep adding points until it goes to 300. No, you cannot do that. You will have only 100 points. You decide whether you want to do a one shot or you want to do 80 plus 20 or 70 plus 30 or 50 plus 50, whichever way it is. Okay. So in this particular case, it is kind of infinite, okay, and then greater than 2:1 or above, roughly about 1:2 or less than 1:2. Okay. If you are talking about k, meaning the dimensions being less than greater than 20, and here it is less than 20. K is the number of dimensions and n is the number of sample points that we are talking about. Okay. So if you can take about greater than 500, let us say, probably support vector regression, no, it is really not telling you that, it is not listed in the order of preference, it just says support vector regression, fixed bases like cubic or thin plate, which is your radial basis, and polynomials, they are just comparing these. Simple landscape, it can handle obviously, complex landscape and local search, fixed basis can also do. Polynomial, there is a question about complex landscape even with 500 samples, there is a problem. Okay. If you have a highly nonlinear stuff, then radial basis obviously is a good way to look at it. Okay. Whereas if you are looking at less than 500 samples and also the dimension is less than 20, they are talking about Gaussian basis, which is basically kriging. Example is kriging. There could be mixed Gaussian process, there are other approaches and others also, right. So if we talk about it, they all can handle all three of these comfortably. It's again, people who like polynomials might just jump on us, but usually polynomials get choked in a few dimensions. Okay. Then interestingly, from an optimization perspective, I want to see, we did not look at the goal seeking and conditional lower bound, but these are just one level higher understanding of these things. Okay. So for instance, kriging kind of an approach can give you this, because these are Gaussian approaches, right. But as I pointed out, what does the Gaussian information give you that the other ones do not give? They give you only the prediction variance based on which you bring all these information, right. But it has also been shown by a paper by Viana et al., probably there is no et al., Viana and probably Hafka and Hafka. There is a paper on how to import uncertainties of your error from one model to another model. So if you want to do SVR, you can use SVR, build it. You also build RBF on the same expression, because you believe SVR can do better in fitting, okay, believe, okay. Then what you can do is you can bring this guy, the errors from this to that, you can import the uncertainties of the errors into the SVR and you can run your SVR, because you believe that SVR will do better for that particular application, okay. So it is quite possible, people have looked at it. Okay. This is one way of, this is just to give you a landscape on what metamodels each metamodel is capable of. Okay. But interestingly, of late this list has grown with the invention of machine learning methods, whatever people call the data analytic approaches or the artificial intelligence. It is basically machine learning approaches is what it is, data mining and machine learning approaches. Okay. So, there are techniques like random forest, decision trees, what else is there? Sorry? Artificial neural networks, and if you are very interested in this, then there are also CNN and deep learning techniques, but these are not very suitable for metamodels because we are always talking about scarce samples. Okay. So, these require a lot of samples. So, you keep building metamodels for 5 years, then you can do a deep learning on the metamodels themselves. Okay. That is possible. What else? Ridge approaches, kind of approaches, and you never know, there are a lot of approaches that are coming in. Okay. So, now interestingly, all these guys can also be used for regression. So, that has opened up an entire stuff. People are looking at with limited number of samples, how can you do, but again, now you cannot pick out one particular method is good for that. For instance, decision tree has a very interesting advantage of it can do a 0-1 binary classification kind of an approach. I mean, not binary classification, it can deal with categorical variables, for instance. Okay. And SVR also can do categorical, kriging can also do categorical, but polynomial cannot do categorical. So, there are some limitations and there are some advantages of these approaches as well. And all these new things that are coming up are all based on statistical learning. So, they all bring this prediction variance kind of, there is no issue with that part. Okay. And probably the rate at which they are growing, we might have better insights also, we might be able to get better insights also, not only from an interpolation, but also from an extrapolation perspective, though that is out of scope for this thing. Okay. So, just before going into the next one, there are also a couple of other things that we are not covering in this course per se. Okay. So, after this I am just going to spend one slide on something called the ensemble of surrogates, which we have briefly discussed earlier. When you have a set of points and you do not know which metamodel is going to work, and let us say that you do not believe this particular slide and you do not know, okay. Then because you need to know whether it is a simple landscape, whether it is a complex landscape, or am I doing a local search, am I doing a global search, you might not know all that. I want a function representation to begin with, that is all your requirement is. Then what can you do? Probably you could use all your metamodels, all metamodels that you know of. Okay. You could probably, that is what the ensemble approach means. So, the ensemble approach is, what it says is, if you have n different metamodels across the design domain, at different points different metamodels might work better. Yeah. So, I guess we might have an example in this case. Yeah. So, for instance, if you take this particular example, this is after the update, does not matter. At this location, your RBF is performing better than your polynomial, but if you go here, though the difference is less, the polynomial is performing better than your RBF. We are just taking the data at par. Okay. If you put one more point, whether this will perform better, whether that is a different discussion. Okay. Just given this figure here, at this particular location my polynomial is performing better here, at this given location my RBF is performing better. But please remember, you do not have this line, you do not have the real graph in real life. Then how do you know that this is performing better or this is performing better? That is where you try to use your prediction variance information. Okay. So, the natural question is, can I use a mix of these metamodels? Okay. So, you cannot formulate a metamodel which is a combination of all this. Instead, you could use all the metamodels together and you use a weighted function. The question in such a weighted formulation is, so let us call it's as simple as this. M stands for metamodel, W stands for the weight. Okay. So, how much weight do I give to a particular meta model? And when I say meta model, it predicts y, let us say. This is all it is, but there are different ways of looking at it. As I told you now, at a location, so then you do this meta model at that x, can I do that? Okay. At an x it will be polynomial, but at another x it could be a radial basis function. So, accordingly the weights will change. Okay. Can I do that? So, there are different ways of looking at these weights. The first, one of the first in this structural domain was proposed by Goel et al. It is an ensemble of meta models kind of a paper. So, these are just ideas, you do not have to worry about the paper per se, but this is an idea to tell you like how you can leverage all the meta models learnings. So, we are talking about the weights here, and this E is your cross validation error. The formulation here, it is interesting, is this alpha and beta. Okay. So, initially he performed some study and the author proposed alpha equals 0.05 and beta equal to negative, but later people even optimized these alpha and beta. So, let us not worry about it. So, what interestingly what it gives here is, it says here is an error for that particular meta model, and here we are talking about the cross validation error. Okay. This is the press RMS that we are talking about, and also it will add some average from the other meta model. There is a error per meta model, which is your EI, and there is an average error. If I have 5 meta models, then I have 5 errors. So, alpha times that. So, how much alpha do you want to give? If this error is less, then I will give less weightage to this guy, but I want to balance that. So, I am also putting a plus beta raised, okay, raised to beta, and finally your weights will be like this Wi star that you get for each of them, and then you sum up all of them. It is just normalization, this guy is just normalization, okay. And you will use these weights to finally run your this thing, okay. Now, what is this E average? That is nothing but the number of meta models divided by the linear sum of your errors for each meta model divided by the average of the errors, that is all it is, okay. It is simple, okay. So, the one thing that you need to remember is this E is nothing but your cross validation error or your press RMS. That is the terminology that we have used in this course. Press RMS is the, okay. Press stands for predicted error sum of the squares, okay. Now, this is one way of looking at the ensemble approach. There is another approach, is there is another paper that says, it formulates it this way: error of the ensemble is WIEI. So, what it says is, if I have a function and let us say I had different meta models, whichever way it is, okay. The ones that have the least error should be given the most weight, which means that that particular stuff, everything else will go to 0. It is more like a direct delta function, okay, and it will equal, if you go and estimate it at that point, it will give you the same value. It will give the least, whatever has the least press error at that point, that will be the meta model that will be selected. In this case, you are still averaging it, because you still believe that there are errors with your predictions as well as with your meta models. So, you are averaging it, but that is not happening here, that is all, okay. So, what this says is, there is a E error, the error ensemble, where P is the number of points, okay, and M meta models, right. So, here you are solving an optimization problem, find the WIs, and your goal is to minimize the E ensemble, which is like this, and please understand this EI is 1 cross P, okay. There are P points, then there will be P errors, and M is the number of meta models that you are talking about, okay. And of course, you want your weights to be equal to 1, okay. There is no this thing like this is a better model or this is a better model. It again depends on your application and how you look at these formulations, whether you want to have a running meta model, what do you say, like a dynamic meta model, or you want a static meta model at each point. That is something that you want to look at, okay. Okay. So, these are the ensemble, and we will wrap up with one case study that we were able to recently publish. We are trying to design a Savonius wind turbine. Do not worry about what a Savonius wind turbine is, it is a vertical axis wind turbine. We are interested in the optimal design, and the process that we have used is an ensemble of surrogates, and of course, like a finite element analysis, we have also used a CFD analysis. Okay. So, all this is about the literature review of the work per se. Okay. So, this is a just a basic representation which we put in a water tunnel. Okay. So, the first step in this was the validation. So, there is a water tunnel. This is the top view of the wind turbine that you just saw. It is really not a wind turbine, it is a turbine at this point. And here is the computational representation of this. As you can see, in a subjective sense, we are capturing the vortices. So, you can see 1, 2, 3 marked in this plot, which are the vortices are generated. So is the case in the computational model also. And then we look at different time stamps and how these vortices are being emitted. Okay. Using that, you can come up with something called a Strohal number. Okay. So, what we do is we take these vortices from the computational model and then we compare, and then we kind of get the same CL in both the cases, which is the coefficient of lift in this case. Okay. Using Strohal number, you can come up with the coefficient of lift. Okay. So, so that is what. So, we kind of look at the experiment and then find out what the Strohal number is for both the experiment and the CFD. Okay. So, that is the first part. So, you first validate your computer model with respect to the experimental model. But then what is it that we wanted to do is we wanted to modify the design a little bit, which is like a C, inverted C in this case, let us say, facing each other. Take a cylinder, cut it into two, move the center. That is what a Savonius turbine is. So, literature shows that a batch type of geometry can give you a better efficiency. So, we wanted to investigate that, number one, and number two is, provided that is the case, then we wanted to optimize the geometry, that is all, and these are the parameters that we are taking. And the approach that we are taking is, because this is a high fidelity computer simulation. So, it takes about few hours, if not a day or so, it takes few hours. But again, in an optimization sense, you do not know where you are going to get locked. So, you do not want to directly connect your finite element model to your optimizer. So, we decided to do a metamodel kind of an approach. So, so as you can see here, we are taking polynomial response, Kriging, RBF. I am saying here model M, it could be anything, as we pointed out now, it could be any of the machine learning techniques, but we are just taking these three in this particular case, and it could be any number. The framework still adapts to that. You get an ensemble and you get a press error for each one of these guys. Using that, you can compare the errors and then choose the best. So, there is one model called the best press, or you want to have the minimal press, whatever it is. Okay. So, the first one is a metamodel building. The second one is a cross validation error validation part, and the other one is the analysis part. So, we will quickly see, because that is not the whole point. So, what we do here, as you can see in this particular case, is error metrics for the different surrogate models, right. So, Kriging, PRS, RBF, weighted average surrogate. We are taking an average, but it is a weighted average. It is not just do all the predictions, take an average. No, it is a weighted average. Okay. So, you look at the press metric. Okay. So, for Kriging it was 0.058, and for PRS it is 0.06, 0.059, WAS was just far better, 0.0018. You want the press error to be as low as possible, right. So, similarly, press RMS was far better, and predicted R squared. You can get a predicted R squared, it is not an R squared, predicted R squared from a press error, and this was far higher compared to these guys. Okay. So, from this what it tells is probably your weighted average surrogate is a better meta model compared to any of these meta models standalone. But there is an interesting finding in this work, we will see. So, these are regular stuff. This is the one that I told you, right, f hat plus delta and all that, and this is your regular polynomial, and this is our radial basis function that we are talking about. So, this is a nested axis plot. Okay. This is one way of visualizing your outputs, but we do not have outputs here. What we did is, So, we took about 86 points with 16 corner points in the 4 dimensions. So, to avoid extrapolation errors, and then we took 70 points across the 4 dimensions, and we generated the LHS based samples. We ran CFD analysis at 86 samples, and this is just an interpolation curve. We are not doing a meta model yet, we are just doing an interpolation trying to understand where this is. Very interestingly, as you can see, we are getting about 0.28 in terms of CP. This is the coefficient of performance that we are talking about, 0.28, 0.28, 0.28 at multiple locations. Okay. Maybe this is also 0.28, this is also 0.28, I do not know. We are just showing you that there could be chances of local optima. Okay. But usually CP does not demonstrate a local optima, multiple local optimas, meaning not local optima, multiple local optima. It is not a high nonlinear function, that is the general understanding. But the model that we are using is a slightly complex situation here. So, hence it could be, there is no study as such, and we are not going into the physics part of it. Okay. We are just taking it at par, building a meta model and trying to see if we can optimize and find a good design. And this also shows basically what we call the contour plot for the surrogate model. So, this is basically theta with respect to d, theta with respect to r, theta with respect to phi. Similarly, phi with respect to the other variables, r with respect to the other variables. So, you can see, and it tells you, for instance, these two are slightly nonlinear. This is all well behaved. These two are slightly nonlinear, not really nonlinear, these are slightly nonlinear. Okay. So, from that what we are doing is we are using, this plot just tells you that there could be multiple local optima. So, you might want to do a meta model with different starting points. Okay. So, we do that and we found some optima, okay, and how it performed is here, for instance, but that is not the focus here, but for the sake of completion I am presenting. This is what we started with initial, and this is the optimal profile. What you need to look at is the pressure contour plot. As you can see, the pressure is less in this case for the same input velocity and all that. So, this is a better design compared to this, that is all you need to worry about. Okay. And then of course, we have the vorticity contours and all that, and we have justifications on why the optimal design is really good. Okay. But that is not the focus here. We are interested probably in this case here. Okay. So, what we did is we took the VOS, we ran the CFD simulation and the surrogate simulation. Okay. At this point, the surrogate chooses these numbers as the optimal design variables, and it gave me 0.29 as the CP. As you remember in today's session, what we did in the beginning is we said f hat is equal to f of x, I hope, and there is a validation step. I go and rerun my simulation and see how good they are, right. 0.3 and 0.29, not bad. So, then we said let us try to do this for the other meta models also. So, we ran them. RBF gave something, it gave you 0.30. Original is 0.3. Okay. Another set of design variables, surrogate 0.29, 0.3, 0.3 and 0.3. This is an interesting output. Okay. Why? Because the VOS as expected, okay, at least minimum guarantee it will give you, it will save you from bad prediction. That is one of the examples that we saw in a couple of classes ago in terms of the pedicle screw design, if you remember. Okay. It will give you that, but in this there is a very interesting output is these guys were nowhere compared to WAS, they were very bad. But what happened is, from a performance of the optimal design perspective, they were not any less, if not better, they were not any less compared to your VOS model. Okay. This is a very interesting output. Okay. But after we did this, we also figured out that people have reported similar results elsewhere in crash simulations. Again, a good meta model is not guaranteed to give you a good optima. Okay. There are different ways of looking at that statement. Similarly, a bad surrogate does not necessarily give you a bad optima. Does it mean that a bad surrogate will give you a good no, might give me a bad. But what is the best thing that you can do? I can only build a good meta model. I cannot build a bad meta model and hope to get a better optima. But I should always remember that I might get a bad optima even with a good meta model. So, it depends what you want to do. Do you want to do a exploitation or do you want to do an exploration? If you want to do an exploitation, then start at a starting point, infill points, go to the zone of interest, explore further, exploit further. Or if you want an overall representation, then put more points. See, for instance, sometimes in the early design stage, people want only this, they do not want anything else. I just need to know if I am going to change. Okay, one thing I did not discuss in detail in this is actually a very interesting plot. I did not go in detail in this. There are actually 4 variables in this plot. Okay. What it says is theta, you take a tile, theta is fixed at 9.5 and phi is fixed at 117.5. Then what is varying? The other 2 variables are varying. You come to this tile, for instance, theta is fixed at 12.25 and phi is 117.5. The other 2 variables are varying. So, if you come out and then look at the x axis, theta is varying across the x axis and phi is varying across the y axis. But again, please understand that there is a limitation. You cannot see more than 4 variables in this plot. That is all you can do. In that sense, the contour plot is slightly better because you can do this for any number of variables. It will only let you compare one at a time. With respect to one. Yeah. So, you take one variable, you can compare it with respect to the other variable, but you can do that with respect to all the variables 1:1 at any point in time. Okay. So, that gives you enough information to start your exploration, which direction, where you want to go, and then if you do an optimization, it kind of allows you to zero in or focus and then you can do this. Okay. So, yeah. So, if you look at it, we have just pretty much used the same stuff that we talked about, your press RMS, the press errors and the R squared predicted and all that. So, this is the optimization problem that we solved. It is observed that the individual surrogates provide almost the same optima as the VAS in spite of performing much lower in terms of error metrics. Qualitative comparisons was also provided, that is to check, but in that case, yes, it did do. Okay. So, this was just to give you an idea that just because your error metrics are good or bad, that does not necessarily translate into a good or bad optima. It is only about your surrogate. Then what you do with your surrogate will govern how you want to go about creating an infill points and get approximations. Okay. So, you cannot have a wish list and get everything done. Okay. You cannot say I want to do both exploration and exploitation, I want optimization, I also want to know where the robust zone is. No, you should be clear about what you want to do. Okay. So, practically this concludes the discussion and the course on surrogates and engineering approximations or approximations in engineering design. So, just to give you a recap, we covered initially some basic concepts on optimization, and we said oftentimes your objective functions and your constraint functions are not available explicitly. In such cases, you might want to construct these functions, and regression approaches have been used classically, and we use these terms called surrogates or meta models, because surrogates means it is a surrogate to the actual model, meta model means it is not a meta model, it is a meta model. So, we are using that, and we talked about how do you go about constructing meta models. So, even before that you need some responses based on which you can construct a meta model. So, in that context we talked about design of experiments, we talked about a simple orthogonal array if I am not wrong, and Latin hypercube sampling. We talked about space filling techniques, we might have spoken about limitations of orthogonal array, and then we discussed about LHS. We did not go in detail much, we might have discussed about the Johnson approach, Mitchell-Johnson approach, and then we would have gone to LHS. Then we talked about 3 steps in constructing a response the surrogate. The first one would be to come up with your data, the data which is again for us it comes from the design of experiment. The second one would be to choose your parameters through a maximum likelihood approach or a least square kind of an approach. You can do that. Usually maximum likelihood is used because of the probabilistic nature of the advanced models. So, you find the parameters and after that you will have to find your error metric, because once you fit your model you want to know how good your predictions are. So, you get your error metrics. So, these are the 3 valid steps that we talk about in meta models. Then we talked about a few case studies, and in today's class we talked about exploitation and exploration, how we use the prediction variance to find out what the infill criteria could be, probability of improvement, expected improvement, all these. We gave the respective expressions as well as the figures to motivate the study for you, because this is a kind of a crash course. So, I do not expect you to know all the expressions in by heart, but at least what does it mean pictorially we discussed all this. Okay. So, this is kind of an introductory course for this, and there is quite a bit of advancement in this, and then the hot piece right now is how to use these machine learning and artificial intelligence techniques to build these guys and do a good job about this whole thing. Okay. So, I hope you enjoyed the course and it is useful for whoever took this course, whether you are in academia or in the industry. I guess Murali's talk would have given you the perspective on where and how people are widely using these approaches in the industry. It is being exclusively used in the industry these days. Even leading softwares have incorporated these approaches. So, it is a good skill to have, it is a good knowledge to possess at this point in time, I guess, but you know, you will have to keep updating it. And if you have questions and you are part of the course, you can raise a question, I will address it. And even after that, if you have questions with respect to the technical content, please write to me and I should be able to get back to you. So, thank you so much for being part of the course, and I hope we meet in a better setup elsewhere. Thank you.